Yes, welcome to Vision Plus and welcome back to this S.4 Mathematics. We are looking at calculus. Now we want to look at integration. Because we said under calculus we look at two main items. One, we look at differentiation, which we have finished. Now we are looking at integration. So, by definition, what is integration? Integration is the reverse of differentiation. In other words, integration is the opposite of differentiation. So the introduction is what we are saying. Integration is the reverse or opposite of differentiation. We are saying it is a reverse or opposite. I'm not saying it is the inverse, not inverse. Okay, it is not the inverse of differentiation, but it is the reverse. Reverse means you are trying to go back, going back. So we are saying, in other words, it is a way of obtaining an original function or expression before differentiation. So we need to get an expression or a function that was differentiated. Okay, that is what we are saying. That is integration. We need to obtain the original function that was differentiated. That is the definition. And before we go into the techniques, this is what we are going to cover. Items that we need to cover. Items to cover under integration. One, we shall do integration of functions or expression. Integration of functions or expressions. Two, we shall dive into integration with limits. With limits, we shall be given functions with limits. And then thirdly, we shall look at areas under curves. Areas under curves. And finally, we look at application of kinematics. Then under that, we shall calculate acceleration, velocity, and displacement. These are the items that we are going to cover. What we must note here is that we shall be dealing with simple functions or simple curves or even simple expressions. Under this stage of integration. This means that we shall not integrate things like exponential curves, ratios like sine, cosine, and tan. We shall not do them. Those ones are in additional mathematics. So, what must we note? We are saying that after integrating a constant result. So let me suppose if I have dy dx as 2x plus 1. This is this function here was differentiated to give us 2x plus 1. But now we need back the function that was differentiated to give us 2x plus 1. What we do here simply is to multiply both sides of the equation by dx, so that dy equals to 2x plus 1 dx. And then from here we say integrate both sides. Integrate both sides. What we have done here is called separating the variables. We have separated the variables. So we are going to integrate both sides. This is the symbol for integration. We shall integrate dy equals to, we also integrate 2x plus 1 dx. So what are we saying here? We shall say that this sign here, this is what we call the symbol of integration. Symbol of integration. Okay. And then the same applies here. Then there is this function here. This is the function we're integrating. This is function being integrated. What about this dx here? This dx here means that we are integrating with respect to x. With respect to x, or with respect to a variable x. That is the meaning of the x. It is the same thing here. This side means that we are integrating with respect to y. Integrating with respect to y, which is the function in this case. So what is very important is the moment they tell you to integrate, you must know this is the symbol of integration. Or wherever you see it, it means that is the symbol of integration. And we are calling that symbol of integration integral. You can just say integral of a function, or you can say integrating a given function. So what do we need to know? After integrating, okay, we are saying that a constant results. Okay, in other words, a constant is formed. That is what we are saying. That is a constancy. What is the purpose of a constancy? The purpose is that, remember, under differentiation, we said when we differentiate a constant, we get 0. Okay? When we differentiate any constant, even if it is 1 million, as long as it is a constant, we get 0. So the purpose of this C here is to give us back that constant that was differentiated to 0. So C is a constant that under differentiation was differentiated to 0. And now we want to recover it. Okay? We want to recover it such that we get the original function that was differentiated. So to get C, to get the constant C, we need the limits of integration. This means that in the first case here, when we don't have limits, we shall not know the value of C. Or in other words, we cannot tell which value was differentiated to 0 under differentiation. So in the first case, we shall just be keeping it as C. Why? Because we don't know the limits of integration. But after getting When we know the limits of integration, then we can be in position to find the constant c, which is a number that was differentiated to 0. And then we get back the original function. Even areas under curves, we shall be given the limits. Application here, we shall be given the limits. Or we can be given conditions that make us to conclude for the values of the limits. We said under this we are only dealing with simple functions and curves. So we shall not integrate the following. One, we shall not integrate exponential functions. Exponential functions. Two, we shall not integrate logarithmic functions or expressions. Three, we shall not integrate sine, cosine, or even tan of given functions. We shall not integrate this.